Hello, I'm just another mathematician, and this channel is for me to share things that I think is interesting and also to practice speaking about math professionally and logically. In this video, we're going to cover covariant derivatives on a curved surface, as well as the idea of parallel transport and how it is defined through the idea of a covariant derivative. So first of all, covariant derivatives are intrinsic objects, which means that if I'm an ant on a giant surface like the Earth, and all I can see is ground surrounding me seems to be flat everywhere, I, the ant, can still measure these intrinsic properties and somehow arrive at the conclusion that I am on a giant sphere floating in the middle of nowhere. Well, probably not the middle of nowhere part, but you know. And the covariant derivative is such a property that can be measured by a smart ant who's willing to walk a lot. And here's how. Covariant derivatives traditionally, or on flat space, you would see them looking like this. This denotes the change of vector field y in the direction of x. And an easy example is probably in R2. I call this the x-axis, and this is the y-axis, and this is at the origin point O. If I have another point, I call it O prime, and I construct another coordinates at O prime. This is x prime and y prime. Because this is R2, because this is R2, I want to leave the prime over there. Because it's R2, and it's a coordinate, it's the same everywhere on R2. It's a grid, it's straight lines everywhere. If I go a unit to the right and then unit to the upper direction, it would be the same as me going a unit upper direction first and then a unit right. It's a grid that does not have curvature, which means that this change from O to O prime in the direction of x would not result in a change of y, which means that in R2, the change of the coordinate y in the direction of x is always 0 because they're the same. But there's something that I did here that does not hold true on a curved surface, which is that I assume this new axis x prime is going to be parallel to the original axis x. I assume that the idea of parallelism is defined by the fact that, you know, they look like they're never going to cross each other. And the fact that at point O, I can construct a new set of coordinates that is parallel to the old ones. And these are not going to stay true on a curved surface. And here's how. This is planet Earth, human standing over here. That is a really ugly human. Sorry. Human, drawn larger than humans are, but, you know, human. I'm going to define a vector over here. Call it V. If I were an alien and I'm looking at planet Earth and I want to define at this point a vector V prime that is going to be parallel to V, then I observe what parallelism means over here and say, why not define it like this? I'll call this V prime. They're never going to cross each other. They're parallel. But if I were a little human standing on planet Earth over here, something weird is going to happen. This vector to this little human is pointed to the right. This vector to this little human is pointed up. So to them, if I were a human who just walked from here over here, then these two vectors, it is impossible for them to never cross over because they're perpendicular right there. So we want a new way of defining parallelism for a tiny human on the surface, not for the alien observing the Earth from far away. So we do that by something called parallel transport. Do I want to explain that right now? I'm not going to explain that right now, but we do so by parallel transport. Parallel transport is a means for us to define what parallelism means on a curved surface, but we're going to focus on covariant derivatives for now, and they're going to become the same thing towards the end of the video. So how do I measure the change in a vector if I were on a point in a curved space? Well, I'm going to call this point P, and I'm going to draw a magnified version of what's going to happen at point P, which is, you know, it's a giant planet. At point P, it might as well look flat. So let this be Earth, let this be P, and let this be the human standing on P. And I'm just going to define it as I'm going to define P as the point that this little human's left foot is standing on. And now I'm going to find a tiny neighborhood, a tiny parcel of land surrounding the point P. I'm going to name it neighborhood NP. Because it is such a tiny parcel of land on such a giant sphere, it might as well be flat. And this is how we intrinsically define tangent vectors. If I take this sphere and expand it out imaginarily, I don't really have to construct like a bridge or whatever, it would look something like this, which is what you see on textbooks and videos, standardized versions of what a tangent plane look like. They may even give it a name like TPM or something. And if this is the manifold M, manifold is basically a two-dimensional object that we're only caring that we only care about the surface. But yeah, this is what you see in textbooks, a tangent plane. And in reality, we don't need a giant thing in order to define it. We only need a tiny parcel of land and a direction, basically. And if I walk some distance to the right, I'll call this distance delta x, a very small distance, and I arrive at a point Q, and again, construct a neighborhood around it in Q. Again, might as well be flat. And I would have defined a tangent plane here called TPM and a tangent plane over here called TQM. Yes, and because this is a small distance on a giant sphere, in my opinion, someone who just walked several steps, TPM is the same as TQM, because they're so close and because I think the Earth is flat as the end, which is the same process we do when we're taking the covariant derivative. If I define, this is an arbitrarily defined derivative, this is an arbitrarily defined vector space, vector field. So I'm just going to define, well, this is y at point P is going to point this way, and somehow magically y at point Q is going to point that way. And I want to know the change of vector field y when I walked a tiny distance in the direction of vector x. Then the covariant derivative would have been constructed as the same as what we want. How we're going to do it is I am going to superimpose these two images, kind of like two pieces of glass, and you put them together. And they are going to stand on top of each other, stacked. And I would be able to see this vector over here. I'm going to call it ghost. I'm just going to draw a ghost next to it. This is ghost y is the superimposed version of y, because in my opinion, TPM and TQM are the same thing. So I can just stack them on top of each other as if I never walked and observe how the ghost and the reality are different. And this is how we define covariant derivatives. Because this is a small step as required when we're taking derivatives of something, we can also assume that the surface is flat, which is an intrinsic property. I defined the neighborhood, which is an intrinsic property, tangent planes, intrinsic property. Thus, the covariant derivative is an intrinsic property that a tiny ant on a surface will be able to define. And then next, I'm going to talk about parallel transport, which is, I'm just going to give the definition first, which is the change of vector field x in the direction of x is 0. Such transformations is called parallel transport. And this is how it works. X is an arbitrary vector field. I can define it as anything that I want. Why not define it as y over here? So this states that if I walk in the direction of this given arbitrary vector field, the change in the vector in the next step that I take is going to be, it's not going to change. It's going to be 0. To make this clearer, just going to drag this over here and then make this little human really walk along y to here. So this is the path that this human just took in the direction of y. And if I want this property to hold true, that the change in the vector field y is not going to change when I take a tiny step delta y over in the direction of y, then on my new tangent plane, which I'll name TP double prime M, my vector is still going to be pointing towards the same direction. It's not going to change directions. It's, again, if I superimpose the two fields on top of each other, it's as if now I get to draw a double ghost. It's as if double ghost is the same as the original vector. It's as if nothing changed. Yes, and this is what we call parallel transport. And an easier way probably to think about it is define, this is the process, for me, the ant. Step one, stand on top of the earth. Step two, identify the point on which your left feet rests. Step three, identify a tiny neighborhood around the point that you just identified and define that as the tangent plane around the point that you identified. Step, I forgot the number. This is why memory is important. But the next step, I've defined the next step. I'm going to hold up a vector v. I'm returning to this part of the page. By the way, so I'm gonna hold up a vector v on my shoulder, whatever, in whichever direction, but I'm gonna fix it at an angle to the tangent plane. And I'm gonna call that angle theta because I'm bad at remembering things. Now, I walk towards the direction of well, I can walk towards any direction, really. I walk towards some direction, but the tangent plane that I think is tangent is always going to be defined by the point that I'm stepping on with my right feet. Again, memory is important. So the tangent point is going to change as I walk, but the angle with which my thing that I'm holding up and the tangent plane is making does not change. So I'm just going to carry this vector over, regardless of how I am walking and where I'm going, it's going to be the same angle. So if we go back to this example, when I walk from point P to let me name this PQ, that is a really ugly Q, point Q, the vector V is going to become vector V, let's name this VP, and this is VQ. This, in my opinion, is keeping the vector pointing towards the same direction in the perspective of the tangent plane as I am walking on a curved surface. And this process of keeping the vector in the same direction in the perspective of the tangent plane is what we call parallel transport. Yes, which is the same as what's happening over here. I'm keeping the vector in the same direction regardless of where I'm going. If I draw a tangent plane over here and call it TQM, then this vector and this vector, if the two tangent planes superimposed on each other, is going to be the same vector. And that is how we know they never change and that it is parallel transport. I think that's all the time I have for this video. Thank you for watching. I'm excited to make more.